Hello, everyone. My name is Georgi Rusev. I am PhD student in Institute of Informatics and Communication Technologies from Bulgarian Academy of Science. Today I am presenting you my last results. Its title is Spectral Feature Extraction from ECoG signals, Impact of Filtering and Window Length. It includes 4 methods, and 2 experiment scenarios related to the NemoBMI project that Petya mentioned. And I work. The methodology includes 4 methods. The first one is temporal windows on row signals, one with 100 milliseconds, and one with 1 second was used in this work. The common average reference filter is employed for filtering row signal, electrocorticographic row signal. And for time frequency representation, the continuous wavelet transform was used. Finally, the Reander curve approach, which reduces feature after continuous wavelet transform, is employed. The common average reference filter is used to pre-process the row signal by reducing noise across electrodes and improve overall signal quality. This filter is a special filter that increases signal to noise ratio. From an algorithmic perspective, it is straightforward. The mean across electrodes is computed and subtracted from each channel, as you can see in the first quotation, where H is total number of electrodes. In our case, it is 64. And SEK is the row signal in the formulas. The continuous wavelet transform being complex exponential modulated by Gaussian gives a good balance between time and frequency resolution, which is ideal for signal where time and frequency content vary over time. The Gaussian envelope ensures smoothness, reducing artifacts, and make it suitable for more detailed spectral analysis. One effective way to interpret ECoG signals for motor control decoding using continuous wavelet transform is by employing Morlet wavelets with fundamental frequencies regularly spaced between 10 Hz and 150 Hz. In this study, these fundamental frequencies were obtained with a 10 Hz step. Two expressed values after Morlet wavelets were obtained in both absolute values in the first quotation and the squared magnitude in the last one, and use it for further feature extraction.
Yes. Could you give an intuition of what this wavelet transform is? Is it a convolution or?
Yeah.
Yes, it's a convolution.
Convolution with the wavelet.
Yes, that's right.
And how does it extract frequency?
It doesn't extract. Frequency is parameter. Yeah.
Well, yeah.
All different wavelets.
Yeah. Thank you. The Reander curve approach combines our fundamental frequencies after Morlet wavelet by reducing computational
Dimension features.
yeah, dimensional frequencies
Features.
and as you can see in the second quantitation, the MIF is a Morlet wavelet transform. The delta if is in the step frequency 10 Hz, and F is our fundamental frequencies ranged between 10 Hz and 150 Hz. This work includes two experiment scenarios.
Go back. So here you are combining.
Our fundamental frequency after.
Ne fundamental.
Pairs of frequencies.
No. He combines convolutions with different frequencies.
Exactly, but you're taking pairs of consecutive.
Yeah.
Yes, and plus one is next.
This is Morlet transformation, not.
Each one of them is one of these Morlet transforms. Now you're taking averages over consecutive transforms. Why? What does this do?
Not average, this is area under curve.
It is
So
area
to obtain only 64 signals.
Understand?
But if you have, this is way to combine all Morlet transforms for different frequencies.
Way to approximate the area under curve.
Yes, this is only area. Georgi, can you write?
Okay.
Because
One moment.
So I is a vector.
yeah.
Well, the area under that curve would be just the sum over I of NFI at this.
Because actually French team worked with the same Morlet transforms, but in this way they extract a lot of features. In order to fit our features to 3D spiking neural network, we have to decrease this. And we were thinking how to combine various Morlet transformations into one. And this is way to obtain, Georgi will explain.
Yes, wait a moment. Frequency. Yeah, okay.
And it appears it works.
Yes, after continuous wavelet transform, we extract 15 wavelet transforms, feature vectors. After that, we calculate for each frequency area under curve. If you have maybe this will.
I understand what an area under curve is, but you're not doing this for individual frequencies. You seem to be doing this for pairs of frequencies, right? And now if you take a sum over all of these,
this combines all frequencies finally.
Yes, why do you do it so complicated? I mean, you could just do a sum over f of mf. This is effectively what you're doing. You see, when you're taking the sum over f and you're taking mf halves plus mf plus 1 half, if you increase f by 1, effectively you're doing 2 times mf halves, which is mf.
Okay, this is also way, but if we
simply a sum over mf.
Actually, I think that Georgi tried summation also. Did you try initially or not?
We don't have experiment with this
No.
variant.
But you see my point, right?
Yeah, I'm
Yes.
sure so.
Twice. Which is the thing.
Yeah, but this is area. If you sum this is area below. This is different than simple
We
summation.
have 15 points and 15 points here, and for each we calculate the random curve. That's
Okay, maybe we do this later.
it is simple.
With the exception of the first to the last one. All the others are just summed up.
But this is areas. Simple summation is different.
Yes.
We will yell different. This is we calculate the area. Yeah, more or less.
They choose the where the conclusion window is the ideal shape with the window or parabola or another shape.
What do you mean parabola?
With convolution.
Convolution is with Morlet function. Morlet function, you know, it is not parabola. It is it has center of frequency and decays around it on both sides. This is Morlet function. This is not parabola.
No, the shape you want to do convolution with the window with another function.
Window is on the raw signal. This is not parabola. Not, this is more or less sinusoidal. This is signal variates, you know, like in EEG data, in ECoG data, you also have variations of signal. Up and down, up and down. It's not sinusoidal, but you can say that this is kind of periodic signal.
Can I continue?
No.
Or have another question?
Okay, continue.
Um, this work includes two experiment scenarios. The first one, to express it, Morlet values are compared, absolute and square magnitude, and two temporal window, one with 100 milliseconds and one with 1 second, are compared. It's important to mention that in case of the 1 second signal, a new 100 milliseconds center around the peak of the Morlet wavelet and used for further feature extraction. Okay.
Do you have picture?
The second experiment is identical as the first one, but with a minor difference. The common average reference is applied to all approaches from the first experiment. The database contains electrocorticographic recording of the brain activity for patients with tetraplegia. While sitting in from the PC, patient watch the avatar. When the avatar state is idle, the patient should be thinking of idle, and when the avatar state is walking, the patient should be thinking of walking. For each two classes, idle and walk, the data is divided into portion of 59 records over period 100 milliseconds for 64 ECoG electrodes. For evaluation statistically, the one way ANOVA was performed using p-values and computed with Python SciPy Python library. Here, the statistical results from the first experiments, it demonstrates that the absolute values approach with 100 milliseconds windows statistically outperform the others on training and on testing data. Here are the second experiments. Here again, the absolute values with 100 milliseconds statistically outperform the others. And it's important to mention that the common average reference filter shows better results that the first experiment without using common average reference filter. That's all.
But I need to come back to this question of 100 milliseconds.
100, okay.
In 100 milliseconds, you can fit in exactly one period of your 10 hertz.
Yes.
There is no wavelet. There is just this oscillation.
Yeah.
There is no dumping, I want to say.
Okay.
Think about it.
Wow.
Yes, but it appears that when we use 1 second, longer period, the distinguishing between two classes is worse.
Yeah, but it's not correct. Then take a bit a longer window or whatever, that one window fits into your sliding window.
Yes, but the main idea here is that when I apply 1 second window, after Morlet, I use a new 100 milliseconds place center around the peak of the Morlet. And these windows 100 milliseconds used for further feature extraction. Yes.
To exclude the side effects.
Yes.
More.
By this way, yes. No. Okay.
More questions?
More questions? No.
Thank you very much.